Hello, welcome to this MOOC on antenna basic parameters. My name is José Manuel Fernández González from Universidad Politécnica de Madrid, and this short presentation is about transmitter antenna parameters. The index of this presentation, we will talk about antenna parameters in a transmitting antenna. So we will first see the input impedance and then see the radiation pattern. Transmitter antenna specifications, we can define a transmitting antenna as a circuit where the parameters we will see is input impedance, radiated power, and efficiency. We can also consider the transmitter antenna as a source of waves. We will define a radiation pattern parameter, polarization pattern, directivity, and gain. And finally, we will talk about equivalent isotropic radiated power. So one of the most important parameters in a transmitting antenna is the antenna impedance. When we feed the antenna by a harmonic signal generator, here, the antenna behaves as a linear impedance load. Here we have the antenna, the transmitting antenna. We can specify the circuit with the input impedance that changes with frequency. So the antenna impedance in function of frequency have a real part, a resistance antenna, and an imaginary part, an input reactance antenna. Here we have the equivalent circuit. We have the generator part, the transmitter, and here the antenna impedance. Another parameter which are related with the antenna impedance is the reflection coefficient. In high frequencies, it is usual to work with transmission lines. In the situation, the load impedance is measured by reflection coefficient. For example, here. The reflection coefficient is the ratio between the backward waves and the forward waves. Okay? Also, the reflection coefficient depends on the input impedance of the antenna and of the transmission line characteristic antenna that we have here. Another parameter, the return losses, is equal to minus 20 logarithmic the absolute value of the reflection coefficient that we have here. We can also define another parameter, which is the voltage standing wave ratio. As we see here, is dependent of the absolute value of the reflection coefficient. Input antenna impedance depends on the frequency. We will see it now. And this is one of the main parameters to define the antenna operation frequency band. For example, here we have a dipole antenna, and here we have the variation of the input impedance in the Smith chart. And here we have the reflection coefficient of this dipole antenna in function of the frequency. Here, for example, the operation band of this dipole are in this area. Input power. Not all the power available from the generator is injected into the antenna. Part of this power is reflected when there is no impedance matching between the generator and the antenna. So we can define three powers. We have the input power or accepted power by the antenna. We have the available power from the generator. And we have the reflected power that we will have here. What we see here, we have the dependence of the square absolute value of the reflection coefficient, which is the reflected power divided by the available power from the generator. Also, the impedance mismatch, which is the input power divided by the available power from the generator. What we can see here also is the dependence of the reflection coefficient of the antenna in terms of the antenna impedance and in terms of the a generator impedance. Impedance mismatch losses can also be defined, which is minus 10 logarithmic 1 minus the square absolute value of the reflection coefficient. Antenna efficiency. Not all the injected power into the antenna is radiated as an electromagnetic waves. Part of the injected power in the antenna is lost in heat. The antenna efficiency is defined as the ratio of the radiated power divided by the power accepted by the antenna. So the real part of the antenna impedance can also be divided into two parts proportional to the radiated and dissipated power. Here we see the antenna impedance and we have antenna resistance, which is divided into a radiation resistance and into a dissipation resistance. So the antenna efficiency can be defined as a ratio between the radiation resistance and the antenna resistance. Okay? Here the antenna resistance is the radiation resistance plus the dissipation resistance. In the far-field radiation of an antenna, the electric field can be modeled as a spherical wave. Here we have, for example, the definition of the electric field in terms of spherical coordinates. We have the electric field in terms of maximum electric field, polarization unit vector, normalized field pattern, and the spherical wave dependence. What we can see here is that the polarization unit vector and the normalized field pattern depends only on the spherical angles and are totally independent of the distance in the far field. The normalized field pattern, the most important part of the field pattern of an antenna, is the absolute value. So field pattern shows the field intensity as a function of the two spherical angles, theta and phi. Here, for example, we have an example of a dipole, and we see here the field pattern in 3D of the dipole. We see also that the absolute value of the maximum of the field pattern should be 1. And here we have the 2D pattern of the dipole. The field pattern can also be expressed in terms of the field pattern, the absolute value of the field pattern. Here we have a graphic representation of different antenna radiation properties. For example, here for a directive antenna, here we have the pattern for an omnidirectional antenna, and here we have the pattern for an isotropic antenna. We see here that the antenna radiated in the 360 degrees around the free space. The references of this short presentation, we use these 5 references for this presentation. I hope you have enjoyed this presentation. Thank you very much for your attention.